So applying the MMC modifier with positional tolerance, let's say with 0.5 millimeters in this example, we are communicating that position tolerance 0.5 millimeters only need to be exact when the feature of size is at maximum material condition at MMC. This means when the pin size is at maximum of 21 millimeters. If our feature of size, like our pin, gets smaller, the allowable position deviation will be increased by the same amount the feature of size decreases from MMC to LMC. And this extra deviation is known as bonus tolerance. To put it mathematically, bonus tolerance equals MMC, actual size. So the total position deviation allowed for the pin will be position tolerance as MMC plus bonus tolerance. So in our case, position deviation equals 0.5 millimeters plus bonus tolerance. If the pin size is at MMC 21 millimeters, bonus tolerance will be 21 millimeters to 21 millimeters. MMC and actual size is same, so it will be 0. Total position deviation 0.5 millimeters. If the pin is produced at 20.5 millimeters, bonus tolerance will be 21 millimeters to 20.5 millimeters equals 0.5 millimeters. So the total positional deviation will be 0.5 plus 0.5 is equal to 1 mm. If the pin is at 20 millimeters, bonus tolerance will be 21 minus 20 is equal to 1 mm. Total position deviation equals 0.5 millimeters plus 1 millimeter equals 1.5 millimeters. If the pin is 19.5 millimeters, bonus tolerance will be 1.5 millimeters and total positional deviation will be 2 millimeters. If the pin is at 19 millimeters, the bonus tolerance will be 2 millimeters and the total position deviation will be 2.5 millimeters. I hope this is so much clear to you. In this video we have understood the concept of MMC with a pin or a shaft, which is an external feature of size. But the same principle also applies to internal feature of size like a hole. When we apply MMC condition to a hole which is an internal feature of size, the concept works similarly. At the MMC of the hole is at a smallest size in this condition. The position of the hole must be more precise because it has lesser space around the hole for the position variation. But as the hole size increases, moving from MMC to the LMC, remember the LMC of the hole is largest hole size. The allowable position deviation increases because there is more space around the hole for deviation without affecting the assembly fit. Let's say this is a motor mounting plate with a central hole for motor positioning, which is a slide fit, and 4 clearance holes for mounting bolts. Here the central hole position is crucial for aligning the motor, so it would not use MMC modifier. However, the 4 mounting holes are mainly for fixing the motor to the plate and do not have critical positioning function. So by applying the MMC to the positional tolerance of these mounting holes, we allow them to have more positional freedom as the hole size increases. If the hole sizes are produced slightly larger than the minimum size, they can be a bit off position while still fitting correctly with the bolts. And this is where the MMC modifier becomes useful in assembly. It provides flexibility by allowing the part to have more positional variation while still meeting the functional requirement. Additionally, the inspection process is simplified with MMC modifier because we only need to verify the virtual condition. For example, if there are 4 pins on this plate and the pin diameter is 20 mm plus minus 1 mm with position tolerance 0.5 mm, the virtual condition of each pin will be 20 mm diameter. Diameter at MMC plus maximum positional deviation 0.5 mm equals 21.5 mm. So if a functional gauge or fixed go gauge with 4 holes of 21.5 mm at nominal distance pass through these holes, this part will be accepted. Nominal L distance pass through these holes, this part will be acceptable. We wouldn't need an adjustable gauge or CMM to inspect. If you are wondering what is virtual condition, so we will dive deeper into virtual conditions and worst boundary condition in the upcoming lesson. On a un grande table,